Optimizing Hole Size for a Hydroponic System, submitted by Adrian Castillo, Nicholas Celeste, Nick Foster, Clint McElroy, and Lovey Sang. The problem statement is as follows. We are to design a water distribution system, and a uniform flow out of each of the holes is desired. Our task is to calculate the necessary diameters of the holes. That provides a uniform flow. The source pressure is given to be 75 kilopascals. The diameter of the pipe is 5 centimeters and is 10 meters long. The spacing between holes was given as 20 centimeters, which means that there are 50 holes to account for. To start solving this problem, a test apparatus was constructed. By viewing the behavior of this system, we could then figure out how to develop an equation that appropriately models it. Here we have 3 holes of uniform diameters. The pressure is the highest at the capped end of the pipe and is reduced at each hole by the outflow of water. The pipe was slightly bent at the second hole, which is accelerating the flow there and making it look as if the pressure might be the highest there. But this is only a shortcoming of the test rig and not an actual indication of ideal behavior. Now an equation can be developed. Because the pressure was the highest at the capped end, we can start from there. Since there are no other forces, the pressure here can be assumed to be equal to the source pressure. The source pressure in our equation can be adjusted to account for head loss. Head loss was calculated by using equation 1032 in our text and using the given values. This number can be converted to pressure loss by multiplying by the specific weight of the fluid at the given temperature. Now we can reduce the source pressure by this number, thus developing a working source pressure. Since there are 50 holes, by the continuity equation, the sum of these holes must equal the source flow, which means that the flow out of each hole is equal to 1/50th of the source flow. Source flow can be calculated by first finding the velocity due to the diminished source pressure by using Bernoulli's equation. Substituting in the actual values, and solving for velocity, and plugging this number in for flow, Q, we now have the source flow. Since the outflow is equal to Q over 50, we now know the value of the flow out of each hole in meters cubed per second. At the last hole, the velocity is the same as the velocity of the source flow. This is because the end of the pipe is a stagnation point, so all velocity here must exit the pipe at the hole. Using these values, the necessary area can be calculated, and from the area, we can calculate the diameter of the hole required to maintain uniform flow at this location. Metric drill bits can be acquired that are accurate to the 1/10 of a millimeter. For the next hole, we know that the rate here is 1/50th less than the flow of the hole before it. By diminishing the source flow by 1/50th, we have accounted for the outflow of the hole to the right of it. And we can then use the same approach that we used at the 50th hole here with the adjusted source pressure. The development here is the same as before, so we'll move quickly. The velocity is calculated, and just like before, the area can be calculated. And finally, the area here can be used to solve for the necessary drill bit. Note that this value is almost the same as at hole 50, which makes sense because the flow here is only 2% less than it is at hole 50. This procedure can be repeated for every hole along the pipe by adjusting Q sub S at each hole by 1/50th of the flow of the hole before it. This type of iterative approach can be done rapidly in Excel. The general equation for the nth hole can be found. We see that the velocity of each hole varies proportionately to the number of the hole, and thus it depends on the location of the hole. Even more interestingly, we can solve a symbolic expression for the necessary area. By substituting and solving for A and making a few obvious cancellations, we see that for uniform flow, the area of the required holes only depends on the number of holes as a fraction of the area of the source pipe. Finally, we can solve this for the required diameter that provides a uniform flow for n holes. This is our solution to the problem. The first hole needs to match the diameter of the pipe. In this case, it is a 5 centimeter hole, and the last hole at the end of the pipe needs to be 7.1 millimeters. To confirm that our calculations were correct, a model was constructed. We decided to construct a much simpler 4-hole system, as our equations work for any number of holes. Here is a video of our model working. The column heights varied roughly as our mathematical model predicted. A slight deviation can be seen at hole number 3, and this was most likely due to imperfections in the drilled hole at that point. We can also see that the flow out of the holes is not laminar for the entire column. and this turbulence would make our height predictions inaccurate. However, we can see that drilling the holes in the determined diameters resulted in a uniform flow distribution, and therefore our model and calculations were successful. This presentation was narrated by Christopher George.